Let's continue. Okay, let me open the table of content first. Wait, there is mosquito. Okay. We are still on chapter 22. Beyond physical memories, policies, and still on homework simulation here. Let's check that out. Okay, we are still on homework simulation here, basically checking out the different policy replacement, something like that. Or the page replacement policy, I mean. Okay, now we will take a look at this. The Valgrind Leaky tool, I guess. I'm not sure if I'm able to understand or how to read the information from this tool. So let's check that out. Okay, this one. Oh, hello Ruchi. How are you? I'm still fine, I guess. Do you know some results to get started with reverse engineering? Oh, I don't really know. Yeah, I don't really know about reverse engineering. But what did you want to reverse engineer? I think what is it called? Maybe you can take a look at LoRaWire. I forgot. Let me check. LoRaWire. What is it called? Reverse engineering, maybe? Yeah, maybe you can take a look at this. I haven't tried watching this. Let me copy this in the chat. Yeah, and I haven't watched this video, but maybe that is something you can get started with. Okay. Wait, what am I again? Valgrind to Leaky, okay. To make this useful. Okay. Valgrind Leaky information, I guess. Oh, there's example. I guess this one. You must specify to Leaky, okay. Leaky is a simple Valgrind tool that does various kinds of basic program measurement. It adds quite a lot of simple instruments to the program's code that does various kinds of basic program measurement. It adds quite a lot of simple instrumentation to the program code. It is primarily intended to be of use as an example tool. Wait, let me copy this in the chat too, in case anyone wants to take a look. Okay, to be of use as an example tool, and and consequently emphasize clarity of implementation over performance. Key command line option. Okay, this is the command line option. Oh. Okay. Oh, that's not what I expect, but an example tool. Let me check this. Am I lagging? I hope not. Okay, maybe we cannot access that. Okay. TRT. Okay, let me check. This mem check. There is mem check here. Okay, screen. Call green. Green, okay. TRT. Mas if. Okay. Oh, that's it. An example tool. So it's like only an example. Is that it? Maybe. Yeah, I'm not sure how to read the data from Leki here. Let me show an example, I guess. Tool Leki trace mem. Yes. And then I think this one. What is this information? Like what is I and what is L and what is S? To make this useful for the simulator above, you'll have to first transform its virtual memory reference into a virtual base number reference, then by masking off the offset and shifting the result bits down. So from virtual memory address or reference into VBN, the virtual base number. Okay, but then how big of a cache is needed for your application trace in order to satisfy a large fraction of requests? I'm not sure which virtual memory reference in here that I should take a look. Is this the one? Maybe. Let me check. Okay, maybe something like this. And then save by 8 maybe. I don't think it is 8. Yeah, we need to save the resulting bits down. You know what? Let me check something like this maybe. Okay, how many is this? How many byte? 37? Yeah, I'm not sure about how to read the information from Lecky tool here. How big of a cache is needed for your application trace in order to satisfy a large fraction of requests? Plot a graph of its working set. Reference trace of every instruction and data reference made by the program ls. Yeah, I'm still not sure about Valgrind Lecky tool here. Okay, maybe I will skip this for now and let's continue, I guess, to complete virtual memory system, chapter 23. Okay. Complete virtual memory system. Okay, wait a minute. Before we end our study of virtualizing memory, let us take a closer look at how entire virtual memory systems are put together. We have seen key elements of such system, including numerous page table design, interaction with the DLP, sometimes even handled by the operating system itself. Okay, how entire virtual memory systems are put together. We have seen key elements of such system, including numerous page table design. Key element of such system, okay, numerous page table design, interaction with the translation look aside buffer, sometimes even handled by the operating system itself, and strategies for deciding which bits to keep in memory and which to kick out. Right, the policy to decide which page to keep in memory and which to kick out. However, there are many other features that comprise a complete virtual memory system, including numerous features for performance, functionality, and security. And those are crux. How to build a complete virtual memory system? What features are needed to realize a complete virtual memory system? How do they improve performance, increase security, or otherwise improve the system? Okay. A complete virtual memory system. I see. So previously we are, I assume, only taking a look at a small part of the virtual memory system, not a complete one. To make a complete virtual memory system, it looks like we need another feature. Maybe something like that. We need other features too. Okay. So when we take a look, maybe just the key point or the main point of the virtual machine system. Virtual memory system. Yeah, sometimes when I think of VM, I usually think of virtual machine, not virtual memory. We will do this by covering two systems. The first is one of the earliest examples of a modern virtual memory manager that found in the VAX/VMS operating system. Okay. As developed in the 1970s and early 1980s, a surprising number of techniques and approaches from this system survive to this day, and thus it is well worth studying. Oh, okay, we will be covering two systems, I guess. The first one is the earliest example of a modern virtual memory manager in VAX/VMS operating system, developed in 1970s and early 1980s. Okay, and still, what is it called? Some of the techniques and approaches still being used to this day. Interesting. Okay, some ideas, even those that are 50 years old, are still worth knowing. Even those that are 50 years old are still worth knowing. A thought that is well known to those in most other fields. Even those that are 50 years old are still worth knowing. A thought that is well known to those in most other fields, for example physics, but has to be stayed in technology-driven discipline, for example computer science. The second is that of Linux. Okay. For reasons that should be obvious, Linux is a widely used system and runs effectively on systems as small and underpowered as found to the most scalable multi-core system found in modern data centers. Thus, its virtual memory system must be flexible enough to run successfully in all of the scenarios. We will discuss its system to illustrate how concepts brought forth in early chapter come together in a complete memory manager. To illustrate how concepts brought forth in earlier chapter come together in a complete memory manager. Okay. Alright. VAX/VMS virtual memory. The VAX-11, I guess, mini computer architecture was introduced in the late 1970s by Digital Equipment Corporation, DAC. Oh, I'm kind of curious. What is the size of the mini computer back then? Yeah, in the late 1970s. Okay. DAC was a massive player in the computer industry during the era of the mini computer. Unfortunately, a series of bad decisions and the advent of the PC slowly but surely led to their demise. Oh, okay. Yeah, that make me wonder. Is the personal computer here smaller than the mini computer during that era, the late 1970s? Maybe. Yeah, I'm not sure yet. I haven't born during the 1970s. The architecture was realized in a number of implementations. The architecture was realized in a number of implementations, including the VAX-11/780. Okay, and the less powerful VAX-11/750. Okay. The operating system for the system was known as VAX/VMS or just plain VMS. Okay. I'm kind of curious what VMS stand for here, and also VAX, I guess. Yeah, just some random stuff. One of those primary architects was Dave Cutler, who later led the effort to develop Microsoft Windows NT. Oh, okay. One of the primary architects was Dave Cutler, who later led the effort to develop Microsoft Windows NT. VMS had the general problem that it would be run on a broad range of machines, including very inexpensive VAX and yes, that is the proper plural. Oh, okay. The proper plural. Alright, I learned something new, I guess. Think very inexpensive VAX and the extremely high-end and powerful machine in the same architecture family. Oh, okay. Thus, the operating system had to have mechanisms and policies that work well across this huge range of systems. Okay. So from the inexpensive one, or maybe the cheap one, something like that, or the budget friendly, maybe not necessarily cheap, the extremely high-end and powerful machine. Okay. Yeah, the operating system needs some kind of mechanism and policy that work across that range. Yeah. As an additional issue, VMS is an excellent example of software innovation used to hide some of the inherent flaws of the architecture. As an additional issue, VMS is an excellent example of software innovation used to hide some of the inherent flaws of the architecture. I assume the architecture in here means the hardware architecture. Maybe. So the software hide some of the flaw from the hardware architecture. Maybe something like that. Although the operating system often relies on the hardware to build efficient abstraction and illusion, sometimes the hardware designers don't quite get everything right. The operating system often relies on the hardware to build efficient abstraction and illusion. Sometimes the hardware designer don't quite get everything right. Okay, in the VIX hardware, we will see a few examples of this and what the VMS operating system does to build an effective working system despite these hardware flaws. What the VMS operating system does to build an effective working system despite these hardware flaws. Okay. So yeah, it looks like the architecture in here means the hardware architecture. Okay. Memory management hardware. Okay, the VAX-11 provide a 32-bit virtual address space per process. Okay, divided into 512 byte bits. Okay, thus virtual address consists of a 23-bit virtual page number and a 9-bit offset. Right, from this one the offset is, so we divide this 32-bit virtual address into what is it called, into a few pages, and one page have the size of 512 byte. That's why the offset is 9 here. So maybe something like this, I guess. Right, 512. So no, not that one. 2 power 9. Right. That's how we got the offset bit here. Just to refresh some memory. Further, the upper 2 bits of the virtual page number were used to differentiate which segment the page reside within. Thus the system was a hybrid of paging and segmentation, as we saw previously. From the chapter, I think this one, chapter 20, section 20.2, hybrid approach, paging and segmentation. Okay. Further, the upper 2 bits of the virtual page number were used to differentiate which segment the page reside within. Thus, the system was a hybrid of paging and segmentation, as we saw previously. 2 bits of the virtual page number which segment the page is set within. Okay. The lower half of the address space was known as process space and is unique to its process. Okay. So there's process space in the lower half of the address space. In the first half of process space, known as P0, I guess, the user program is found, as well as a heap which grows downward. Okay, so we split the process space into two, I guess. The first half of process space is where the user program is found, as well as the heap which grows downwards. And the second half of process space, the P1, we find the stack, okay, which grows upward. Well, I guess downward or upwards depends on, what is it called? Depends on where the lower and higher address, I assume. I'm still not sure yet. Let's continue first. The upper half of the address space is known as system space. Okay. Then let me illustrate this, I guess. So let's say we have 32-bit, right? The space. Our half, what is it? Half, something like this. Or maybe let's just call this process space, right? And then inside this process space, we have P0 for where the user program, I guess, user program memory, maybe including heap, and then there is P0, P1, where the stack memory, maybe something like this. That is the lower half, and then there's also the upper half, system space. System space, although only half of it is used. Okay. So in the system space, we only use half of it. Maybe something like that. Half, upper half. Usually only use half of it, question mark. Okay. Protected operating system code and data reside here. and the operating system is in this way shared across process. Shared across process. Protected operating system code and data are set here, and the operating system is in this way set across process. Oh, okay. Protected operating system code and data reside in system space something like this, and those data shared across. Okay, it's process. Maybe something like that. One major concern of the VMS designer was the incredibly small size of bits in the VAX hardware, 512 bytes. Okay, this size chosen for historical reason has the fundamental problem of making. Okay, wait. Major concern is the small size of the bits of small size of the bit size, I guess. Only 512 byte. This size chosen for historical reason has the fundamental problem of making simple linear base table excessively large. This size has the fundamental problem of making simple linear base table excessively large. Thus, one of the first goals of the VMS designer was to ensure that VMS would not overwhelm memory with page table. Yeah, we talk about this, or we learn about this in chapter 20, in case anyone wants to revisit that. Basically a few solutions to make, what is it called? The page table not too large, something like that. Okay. To ensure that VMS would not overwhelm memory with page table, the system reduces the pressure page table placed on memory in two ways. First, by segmenting the user address space into two. Okay. The VAX -11 provides a page table for each of these regions, P0 and P1 per process. Okay, let me VAX/VMS virtual memory, I guess. Be something like this. Maybe. Okay. First, by segmenting the user test space into two, the VAX test enable provides a page table for each of these regions, P0 and P1 per process. Thus, no page table space is needed for the unused portion of the address space between the stack and the heap. Okay, the base and bound register are used as you would expect. A base register holds the address of the base table for that segment, and the bounds hold its size. That is the number of base table entries. Second, the operating system reduces memory pressure even further by placing user page table for P0 and P1, thus two per process, in kernel virtual memory. Thus, when allocating or growing a page table, the kernel allocates space out of its own virtual memory in segment S. I think segment S is the system space, right? This one. Okay. If memory comes under severe pressure, the kernel can swap paths of this page table out to this, thus making physical memory available for other use. Putting page table in kernel virtual memory means that address translation is even further complicated. For example, to translate a virtual address in P0 or P1, the hardware has to first try to look up the page table entry for that page in each page table, the P0 or P1 page table for that process. To translate a virtual address in P0 or P1, the hardware has to first try to look up the page table entry for that page in each page table, the P0 or P1 page table for that process. In doing so, however, the hardware may first have to consult the system page table, which live in physical memory. Oh, okay. So I assume when we want to look up the page table entry in the user, what is it called? User space, user process, I guess. The process space, the process space, where is it? Okay, to translate a virtual address in P0 or P1, the hardware has to first try to look up the page table entry, the PTA page table entry for that page in each page table, the P0 or P1 page table for that process. Okay, what is it called? The process space, I guess, looking up the page table for the process space, but in doing so, however, the hardware may first have to consult the system page table, which live in physical memory. With the translation complete, the hardware can learn the address of the page table and then finally learn the address of the desired memory access. All of this fortunately is made faster by the VAX hardware managed TLB, the translation look aside buffer, which usually or hopefully circumvent this laborious lookup. Oh, interesting. The operating system reduces memory presence even further by placing the user page table or the process space, I guess, the P0 and P1 in kernel virtual memory. Thus, when allocating or growing a page table, the kernel allocates space out of its own virtual memory in segment as the system space. Right, okay. Interesting. So we are using the kernel virtual memory. That's why, what is it called? We need to consult the system page table first, just to look up for the page table entry information. Yeah, that's quite interesting. Okay. Aside the cost of generality, should I read the aside first or? Yeah, maybe I should read the aside first. Aside the curse of generality, operating systems often have a problem known as the curse of generality, where they are tasked with general support for a broad class of application and system. The fundamental result of the curse is that the operating system is not likely to support any one installation very well. In the case of VMS, the curse was very real. Oh, okay. As the VAX-11 architecture was realized in a number of different implementations, right? Can from the previous information here, from the inexpensive or maybe the low-end model, something like that, to the high-end model of the machine, right? The VAX-11 architecture was realized in a number of different implementations. It is no less real today, where Linux is expected to run well on your phone, a TV set-top box, a laptop computer, desktop computer, and a high-end server running thousands of processes in a cloud-based data center. Right. The curse of generality. You know, there's a saying, maybe something like that. One size fit all, fit nothing. So basically, the generality, which means that we are not likely to support any one installation very well. Okay. Hello, Unreal Wines. Is there a difference in how single channel and dual or stable memory works? I'm still not sure about that. I mean, we are currently only talking about the concept, maybe what is it called? Basic concept of the virtual memory. And we haven't talked about channel yet, at least. Maybe we will talk about that when we going to the concurrency. Maybe. But yeah, I'm still not sure yet. Okay. So how does a 64-bit operating system handle all 32-bit programs? Send it ahead. That's if they run simultaneously. Maybe. Yeah, I'm not sure what's happened under the hood, right? Again, this book is still the basic. What is it called? The basic concept. We haven't even talked about the. What is it called? About the specific architecture like 32-bit or 64-bit. But I assume maybe the operating system can handle 32-bit program because it is a subset from a subset in the 64-bit. But yeah, I'm still not sure yet. Send it ahead, that's if they run simultaneously. Maybe not. I mean, the operating system trying to handle a lot of stuff, so maybe the operating system designer are editing about that. But yeah, I'm not sure yet. Okay, so why is Apple why is Apple operating system based better at memory management like Android? It has a lot of RAM. What technology makes the difference? Okay, I cannot answer that question too. Your question is too advanced for my current knowledge. What is Apple operating system is better at memory management? Wait, yeah, I'm not sure about your last question. Why is Apple operating system based better at memory management like Android? Like, did you mean iOS? Maybe. I mean, I don't think Android is the Apple operating system. Yeah, what technology makes the difference? I am not sure what the difference between iOS and Android, Alright. Real address space. Okay. You know what? Let's continue this on the next session. Yeah, I need to digest this information first. Alright, so that's it for now. Thank you for watching and see you next time. Bye bye.